Okay, so if we take a look at number one, again, it tells us that this is propanoic acid. So it's telling us in the prompt that CH3CH2COOH is an acid. So that should help us kind of identify what's the acid and what's the base on the left side. But even if it didn't tell us, just take a look at what has to happen to get from the left side of the equation to the right side of the equation. This is a Bronsted-Lowry acid-base reaction. These are the acid-base reactions that we look at in AP. And you'll notice that propanoic acid actually loses the H on the end. This is an organic acid, so it's one of those that has the H on the end. So it loses its H. That means that this is the acid. It donates its H plus to water. Once it donates its H plus as the acid, it becomes the conjugate base. So propanoic acid is the acid. Water is accepting the H plus, so it's the base. That makes the propanoate ion the conjugate base, and H plus is the conjugate acid. So I labeled acid base, conjugate acid on my piece of paper that I was working through this on. And then based on that, you're giving just one of the pairs. You could have either given propanoic acid and its conjugate base, or you could have given water and H3O plus. You cannot mix and match them. Remember that a conjugate acid-base pair differs by one H plus, just one. It doesn't differ by two. It looks like the same substance, but differs by just one proton, one H plus. So that's part A. And then part B says determine the value of Ka for propanoic acid at 25 degrees Celsius. So determine the value means that we need to calculate it, right? We can't just look it up in Appendix D. So if we need to calculate Ka, remember, this is a weak acid. Notice the double arrowed exists at equilibrium. Well, we're calculating Ka, we're calculating the equilibrium constant for this weak acid. So I kind of set it up down here to get you started with part B. So if we write the Ka expression, it is CH3CH2COO minus times the concentration of H3O plus over the concentration of propanoic acid. Notice water is not included. Water is a liquid. So I set up an ice table right underneath. I rewrote the equation so that I could set up an ice table. I just put an X through water because it's a liquid. Liquids, solids do not play a role in our ice tables. Now, we have to be able to fill this in. So I'm going to give you some hints to fill in your ice table. You can actually fill your ice table in completely, which you need because if you're solving for Ka, you need to know all of these equilibrium concentrations. So they tell us that it's a 0.2 molar solution. It's a 0.2 molar acid solution. So my initial concentration of the acid is 0.2 molar. That's going to go in the initial right under the acid. We're going to have 0 for both of the ions. We don't have any of the ions initially. We just have the acid. But then they give us the pH. Remember yesterday we talked about how the pH gives us the H plus concentration at equilibrium. So you can figure out the H plus concentration. Remember, this equation is not on the equation sheet, but if you have the concentration of H plus equals 10 to the negative pH, that's how you can find H plus concentration. So if you use this pH of 2.79, you can figure out the H plus concentration at equilibrium. Well, now you have an initial and an equilibrium amount. You can fill in the rest of the ice table. So see if you can use that information, the initial concentration of the acid and the pH, which gives you H plus at equilibrium. See if you can use that to fill in the ice table and then use the equilibrium row to solve for Ka. So I'll give you a couple minutes. See if you can fill that in. And as always, if you're working through and you have questions, you can type them in the chat. I can definitely pay more attention to the chat today since you guys are the only ones in front of me. So if you have questions, right, type questions in the chat because you never know if someone else is going to have the same question. But right now, try to fill in that ice table. You have the initial because it's 0.2 molar of the acid. 0 for the ions. And you can figure out H plus at equilibrium because they give you pH. 10 to the negative pH is how you can find H plus concentration. So if we take a look, I filled in the ice table, so you can look down here. I filled in the ice table. So 0.2 molar initial 0 and 0 because they gave us the concentration of the acid. Then remember that pH gives the H plus or H3O plus. Those are the same. H plus and H3O plus are the same. So pH will give us that concentration because the pH gives us the H plus or the H3O plus concentration at equilibrium. So I used 10 to the negative pH to solve for my H plus concentration, which was 0.00162. So that gave me my equilibrium concentration of H plus. Well, if I have initial and I have equilibrium, I can figure out my change row. Because to get from 0 to 0.00162, we have to add that much. And once you have one of the change parts of the ice table, you can fill in the rest because the change row is based on stoichiometry. They're all a 1-to-1-to-1 ratio. And so that means that they're all going to change by the same amount. However, the acid will decrease because it's on the opposite side of the arrow. So when you figure out the equilibrium rows, the equilibrium concentrations, the acid is 0.198 molar. And then both of the ions, so H plus and then the conjugate base of the acid, they're both 0.00162. And so when we plug into the Ka expression, 0.00162 squared over 0.198, we round to 3 significant figures, probably should have rounded to 2, but 1.33 times 10 to the negative fifth. So 1.33 times 10 to the negative fifth. If we round to 2 sig figs, that would just be 1.3 times 10 to the negative fifth. So when we're finding anything regarding a weak acid, tomorrow we're going to do examples on weak bases. I just wanted to be able to have all of the space on the whiteboard at school to be able to do the weak base calculations. So tomorrow we'll look at the weak base calculations, but whenever you're focusing on anything that is weak acid or weak base, it's going to benefit you to use an ice table. Even if you fill it in completely, it is going to be beneficial. There are times on free response questions. So for example, on this free response question, you actually got points for filling in the ice table. Even though you really just needed the equilibrium row, you got points for filling it in. Okay, any questions on how we got any parts in either part A or part B of the do now? Like always, you can type in the chat. You can unmute, right? Whatever you need. I don't have to be worried about connected to the projector or anything. So if you have any questions, just make sure that you ask them. For today, we're going to be going through 3 examples. So we're not going to get to all of them that I had talked about yesterday. We'll just do a couple more tomorrow. So today we're going to do examples 16, 19, and 20. So 16 and 19 are from video 7.3, and example 20 is from last night's video from 7.4. So we're going to be going through those 3 examples. You will want a calculator. I tried doing this ice table on the do now on my phone, and it was much more difficult than if I just had a calculator. So you'll want a calculator and your notes and Appendix D. So lucky me, I left Appendix D at school. So I have it pulled up on my computer. So when we need Appendix D, I can reference it if needed. Appendix D is on Google Classroom, and it's also actually in case you do need it. So if for some reason you need Appendix D, I'll actually just put the link in the chat right now because I have it pulled up on my computer. So there's the link for the PDF of Appendix D if needed. So as we go through today's examples, I'm going to probably go back and forth between presenting my screen and just having me up because I am recording this, and so I want to make sure that my whiteboard behind me can be seen as well. I would recommend pinning me just in case. If you pin me, it'll make it nice and big on your screen so that you can read the whiteboard. If there's any part of the whiteboard that you can't read, just let me know and I can definitely like reread it. I was trying to make sure that I was writing big enough, but still saving some space for us to work through problems. So we're going to actually start by going through example 16. So in your notes, if you flip to your example pages, we're going to go through question 16 or example 16. I can actually tell you exactly what page this example is on. This is on page 18 of the notes. So example 16 is on page 18 of the notes. So I'm going to back up a little bit so that you can see. So example 16, if you want to make yourself a note, this is actually like numbers 28 and 34 of mastering. So this is like 28 and 34 of mastering. And example 16 is actually asking us to calculate the percent ionization. So it says calculate the percent ionization of 0.4 molar hydrozoic acid HN3 solution. The Ka for this acid is 1.9 times 10 to the negative fifth. So a few things. The first thing that I want you to do is I want you to write the acid dissociation equation. Right? You do not have this written in your notes. I was trying to write some extra information to save us some time as we were working through these examples. So you have the question in your notes. What I want you guys to write down is the acid dissociation equation. So this is a weak acid. HN3 is a weak acid. Weak acids exist at equilibrium. So hydrozoic acid is at equilibrium with H plus and N3 minus. And I even put the states of matter just so that we remember that weak acids are aqueous and ions are aqueous because they come from solution. Now, the problem is asking for percent ionization. So I'm going to underline percent ionization. I wrote the equation for percent ionization down here, again, to save us a little bit of time. Somewhere around example 16, I would not recommend right underneath the equation because you'll notice that I have an ice table set up and ready to go. But somewhere, write down the percent ionization equation. This equation is not on your equation sheet, but you need to be able to use it. So percent ionization is how much does the acid ionize? What percent of the acid actually ionizes? Now for weak acids, it's usually less than 5%. So it's going to be somewhere less than 5% for a weak acid. Strong acid should be 100%. But when it wants percent ionization, the way that we calculate percent ionization is the H plus concentration at equilibrium. So here's where our ice table comes in. We need something at equilibrium. So H plus concentration at equilibrium divided by the initial concentration of the acid times 100. So if we think about what we have right now, I want to calculate percent ionization. So I'm just going to do percent ion just to shorthand. Right now, based on the problem, calculate the percent ionization of a 0.4 molar hydrozoic acid solution. I have the initial concentration of the acid. I have the initial concentration of the acid. What I don't have and what I need is the H plus concentration at equilibrium. So in order to finish off this percent ionization calculation, I need H plus at equilibrium. I need that value right there from the ice table. So let's fill in the ice table and let's see how we can find delta H, H plus. So this is a 0.4 molar hydrozoic acid solution. So the initial concentration of the weak acid is 0.4 molar, right? 0.400. That's from the prompt. Nothing about ions initially, so those are 0. Now, it doesn't say anything else. It doesn't give us pH. It doesn't give us anything else about equilibrium. All it gives us is Ka. So we're going to use X's. So we will subtract from the weak acid. We will add to the H plus and N3 minus side. It's a 1-to-1-to-1 ratio. So it's just minus X plus X plus X. So for my equilibrium row, I get 0.4 minus X, X, and X. Now again, my goal is to solve for what I underlined. My goal is to solve for the H plus concentration at equilibrium so I can plug it into percent ionization. So over here off to the side, I'm going to use the Ka expression because Ka gives us information at equilibrium. That's our equilibrium constant. So Ka, I'm going to write the expression first. Products over reactants, everything is aqueous. So H plus N3 minus over HN3. Ka is 1.9 times 10 to the negative fifth. H plus times N3 minus, that's X times X, so X squared, over 0.4 minus X. Now remember, when you look at this, you're like, oh, this looks like the quadratic. But if K, right, if K is smaller, if it's less than 1 times 10 to the negative fourth, we can neglect X. We can assume X is small. So since this is a smaller number than 1 times 10 to the negative fourth, right, negative 5 is less than negative 4, we're going to assume X is small. If you assume X is small, you have to write it down. So I'll just make myself a note up here. Assume X is small. So we're assuming X is small. What that does is that allows us to ignore the minus X. We're assuming that X is such a small value that it's not going to impact the initial concentration of the acid. So now we have 1.9 times 10 to the negative fifth equals X squared over 0.4. So now I'm going to use my trusty calculator. 1.9 e negative 5 times 0.4. I'm going to take the square root of that. X. We'll use 3 sig figs. 0.00276. 0.00276. There's X. Now you have to think about what X is and what you're trying to find. That's why I always like underlining information from the ICE table. When I underline this, that tells me X is what I was trying to find. 0.00276 molar. Now I'm going to go back up. Percent ionization. My final answer is percent ionization. Well, see, I started the percent ionization equation down here. I needed X, I needed H plus so that I could find percent ionization. So what percent ionization is showing us is it's showing us how much H plus we have at equilibrium. So once this weak acid reaches equilibrium, how much H plus do we have compared to how much acid we started with? That's percent ionization. So I'm going to do 0.00276 divided by 0.4 and multiply by 100. I guess if we keep 3 sig figs, 0.690%. Percent ionization has the units of percent. My box got a little crooked there. 0.69%. That means that this weak acid only ionized 0.69%. So if you have 100 molecules, 100 molecules, only 0.69 of them will separate into their ions. The other 99.3%, right? The other 99.3 molecules stay together as weak acid molecules. So this doesn't ionize very much. So that's looking at percent ionization. And something to keep in mind is the higher the percent ionization. So I'll write it over here. The higher the percent ionization, the stronger the acid. So the higher the percent ionization, the stronger the acid, because think about it. Strong acids ionize 100%. Strong acids ionize 100%. So the higher the percent ionization, the stronger the acid will be. This is a pretty weak acid. It only ionizes 0.69%. So that's looking at example 16. As you look through example 16, are there any questions? So again, we were using the ICE table for the weak acid to calculate something at equilibrium. We were calculating H+. So yesterday we looked at how we could calculate pH, which needed H+. But instead of pH, we were calculating percent ionization. Again, make yourself a note. Percent ionization is a formula that you need to know, but is not on the equation sheet. So percent ionization is H+ concentration at equilibrium divided by the initial concentration of the acid. Any questions? All right, so then we're going to look at example 19. So we're going to skip 17 and 18 for now. The only reason we're skipping it for now is because, again, I don't have enough whiteboards to go through these examples like I want. And so we'll just do 17 and 18 tomorrow. And then, we'll do 17, 18, and then the examples that go along with video 7.5. So if we flip to page 19, right, flip to page 19. Page 19 has example 19 at the top. So this example we're going to do right on the screen. So for this example, it says, although the acid dissociation constant for phenol, so acid dissociation constant, this is Ka. So although the acid dissociation constant for phenol, so Ka, is listed in Appendix D, the base dissociation constant for the phenolate ion is not. So again, what this is saying is that the acid dissociation constant, Ka, is given in Appendix D. But Kb for the conjugate base, because if we take a look, the phenolate ion is the conjugate base of the acid. So Ka for this acid is given, but Kb is not. And we can actually take a look. So let me pull Appendix D over so that we can take a look at Appendix D with, all right, so let me zoom in a little bit. All right, so on Appendix D, and if you have Appendix D, you can see on yours as well. I'm just pulling it up on the screen. In Appendix D, on the front page, these are all the Ka values. So notice here, phenol, we have our Ka value. So for phenol, we have our Ka value 1.3 times 10 to the negative 10. But if we flip to the back page where the Kb values are, right, table D2 has Kb values. Notice that that phenolate ion is not there. So Ka is given here, but we don't see the Kb value in Appendix D, and it wants to know why. So the reason that we don't see every Kb value in Appendix D is because for any conjugate acid-base pair, Ka times Kb equals Kw. So again, when you have a conjugate acid-base pair, so phenol is a weak acid. It's telling us it's a weak acid because it's talking about the acid dissociation constant. So phenol is a weak acid. The phenolate ion, notice how it looks similar. The only difference is that this has one less H+. This is the conjugate base. So for any conjugate acid-base pair, Ka times Kb equals Kw. This equation is on your equation sheet. Ka times Kb equals Kw is on your equation sheet. So if you have the Ka of an acid, you can find the Kb of its conjugate base by using this equation. We're assuming 25 degrees Celsius unless they tell us otherwise. So unless they tell us that it's at a different temperature and they give us a different Kw, we assume that it's 1 times 10 to the negative 14th. So then part B says calculate the Kb for the phenolate ion. So in part B, let's use the equation. So Ka, we just said, was 1.3 times 10 to the negative 10. Right, that was in Appendix D. So Ka is 1.3 times 10 to the negative 10. We're solving for Kb. Kw is 1 times 10 to the negative 14th. So if we want to solve for Kb, we manipulate the equation. Kb is Kw over Ka. We assume Kw is always 1 times 10 to the negative 14th. We assume we're at 25 degrees Celsius. So if we do Kw, 1 times 10 to the negative 14th, divided by our value of Ka, and again, this value of Ka came out of Appendix D. So this value of Ka came right out of Appendix D. When we divide the two, our Kb value is 7.7 times 10 to the negative 5th. So if I do Ka times Kb to check my answer, it's going to be close to 1 times 10 to the negative 14th. Maybe a little bit off because of rounding, but it's going to be close. So if you have Ka of a weak acid, you can find Kb of the conjugate base using Ka times Kb equals Kw. Then part C, is the phenolate ion a weaker or stronger base than ammonia? So is the phenolate ion a weaker or stronger base than ammonia? Now, when you want to compare bases, you want to compare the strength of bases, you're going to compare the Kb values. So you want to compare the Kb value of phenolate, which we just calculated here, to the Kb value of ammonia. And you can find the Kb value of ammonia in Appendix D. So if you have Appendix D, you flip to the back. Your Kb values are in the table up at the top, right? Table D2. Take a look at Appendix D and see what the Kb value is for NH3. So you're comparing, right now you're looking for the Kb value of NH3. You should see that it's 1.8 times 10 to the negative 5th. So when we want to compare bases, we need to compare the Kb values. If you want to look at the strengths of acids, you would compare Ka values. Because the higher the K, the more it dissociates and the stronger it is. So if we're comparing Kb, the Kb for phenolate is 7.7 times 10 to the negative 5th. We just calculated that in part B. Kb for NH3 is 1.8 times 10 to the negative 5th. So notice they're both times 10 to the negative 5th. So we're just going to compare the numbers in front of the scientific notation. 7.7 compared to 1.8. 7.7 is a greater number. So the Kb for phenolate is larger than the Kb for ammonia. That means that phenolate is a stronger base. So again, something that you can write down next to this example is that the larger the value of K, the more it dissociates, and the stronger the base or acid. So the higher your value of K, the more it dissociates, because that's what this represents. products over reactants. So the larger your value of K, the more products you have, the more it dissociates and the stronger the acid or the base. Okay, so that's comparing Ka and Kb. Comparing Ka and Kb, looking at how we can calculate one if we have the other, and then how we can actually compare the strengths. So we can compare the K values. So either Kb for bases or Ka for acids. We can compare those values and we can see which one is stronger, because the larger the value of K, the more the substance dissociates, and so the stronger either the acid or the base. Okay, any questions on example 19? Because we're going to kind of switch to video 7.4. Okay, let's see. Yes, question. The top value in part B. So this is Kw. So remember on your equation sheet, Kw is 1 times 10 to the negative 14th. That's the autoionization of water. So that's a constant. Kw is a constant. 1 times 10 to the negative 14th is a constant. Yeah, it's always the same. Yep. Yep, you're welcome. Any other questions? Yeah, and if you continue to have questions, keep them coming. What we're going to do now is we're going to shift to video 7.4. So video 7.4 was on whether a salt is acidic, basic, or neutral. And I will tell you, as you are looking at salts, it takes practice. It takes practice to look at a salt and determine, is it acidic, basic, or neutral? So when we're looking at a salt, remember a salt is any ionic substance, metal and a non-metal, or a metal and a polyatomic, or two polyatomic ions. When you're looking at a salt, you want to split up the salt to determine whether something is acidic, basic, or neutral. So we're going to actually, as we look at an example, we're going to actually split up the salt and we're going to look at first, where do the parts of the salt come from? So the cation always comes from the base, no matter what. The cation of the salt always comes from the base. A salt is produced in an acid-base reaction. So the cation always comes from the base. The anion always comes from the acid. And so we have to look at what base does the cation come from and what acid does the anion come from, because this is looking at conjugates. So when we're looking at the anions, we're looking at those conjugate bases of the acids. And again, it just takes lots of practice. But if you have, for example, a neutral cation and a neutral anion, that's going to give us a neutral salt. Because if the cation comes from a strong base, it's neutral. The anion comes from a strong acid, it's neutral. An example is NaCl. If we have a neutral cation, so that means that it comes from a strong base like Na plus or Li plus. And you have a basic anion. So that means that it comes from a weak acid, because remember, a weak acid has a weak conjugate base. Well, basic outweighs neutral, so it's a basic salt. If you have a cation from a weak base, that cation is acidic. And so if you have a neutral anion from a strong acid, something like Cl minus, well, acidic is going to outweigh neutral. And it gives us some examples. Now, when you have an acidic cation and a basic anion, that is where it really depends. So if we have something like NH4 plus, which comes from NH4OH, that's not a strong base, it's not part of the B on the periodic table, and we have something like Cn minus from HCN. Well, if you have an acidic cation and a basic anion, the acidity or basicity of the salt depends, because they can be either acidic or basic based on the K values. We're going to look at an example, but what you have to do is you have to compare the Ka of the cation and the Kb of the anion. and whichever one is larger, that's what the salt's going to be. So if Ka is larger, that means it's more acidic. If Kb is larger, it's more basic. So when we're looking at this NH4CN example, when we're comparing the Ka of the acidic cation. We're comparing the Kb of the basic anion. Since Kb is larger, the solution overall will be basic. And I know when you're looking at this, you're like, yep, okay. But we're going to look at an example, and we're going to focus on splitting the salt. So we're always going to focus on splitting the salt. Now, will you have to look at this Ka and Kb for one, maybe? But typically we're focusing on one of them being neutral, and then the other one will either be acidic or basic. So what we're going to do is we're going to look at example 20. So example 20 is on page 19. So for example 20, let me move this first whiteboard. Example 20 is like number 37 of mastering. So if you want to make yourself a note, number 20 is like 37 of mastering. So I have example 20 up on this whiteboard. I'm going to back up so that you can see this whiteboard. And I'm going to get a couple different colors to use so that we can really focus on these salts. So example 20 says, predict whether aqueous solutions of the following are acidic, basic, or neutral. So we're predicting whether these salts, because these are all salts, cation and anion, cation and anion, cation and anion, they're ionic substances. So we're predicting whether they're acidic, basic, or neutral. Now what we have to do is we need to split up each salt. We need to split it up. And when we split it up, we need to figure out where does each part come from. So I'm going to split up part A. All right, and I know it's a very light dotted line, but let's do this. There we go. So I'm splitting up this salt. I'm going to focus on the cation and I'm going to focus on the anion. The cation always comes from a base. So add OH when you're looking at where it comes from. So NH4 comes from NH4OH. Right? NH4 comes from NH4OH. It's the cation of the base. Br minus comes from HBr. Here's how we get the salt. I'll show you the acid-base reaction. If I react these two together, NH4OH plus HBr, if I react these together, it's a double replacement reaction. NH4 is going to combine with Br minus, and then we get H and OH, which is water. An acid-base reaction produces water and a salt. So what we're doing is we're focusing on where each part of the salt comes from. So if we think about NH4OH, look at your periodic table. Let's see, do I have one here? Right, sure do. Right, here's your periodic table. You have the B on the periodic table. NH4 is not part of that B, so it's not a strong base. So NH4OH is a weak base. If NH4OH is a weak base, those pairings still hold true. NH4OH is a weak base, and that means that NH4 plus will be a weak acid. Now I know that NH4 plus is not a conjugate acid like we've been looking at, but it is considered an acidic cation because it comes from a weak base. Now if we look at HBr, now you have to think about your 7 strong acids. HBr is one of your 7 strong acids. If HBr is one of the 7 strong acids, Br minus is neutral. Br minus is actually the conjugate base. It's neutral. You still can only have a weak or strong neutral pairing. So HBr is a strong acid, Br minus is neutral. So now if we're figuring out if this salt is acidic, basic, or neutral, now we're comparing what we wrote up on the top. We have a weak acid, so we have an acidic cation and a neutral anion. Well, neutral we ignore. Right? Neutral is not going to have any effect. So if the cation is acidic, that makes the overall salt acidic. So part A is acidic. Right, part A, NH4Br, that's an acidic salt. Let's look at part B, right? So let's just keep going through, let's talk through it, and let's practice. So part B, we have FeCl3. So I'm going to split it in half. I'm going to split it in half, and I'm going to focus on where each part comes from. So the cation always comes from a base. So Fe will come from a base. Add OH to the end. Now, Fe is a little more tricky because it's a transition metal, but if you reverse, Fe is +3. So this Fe is +3, which means it's FeOH3. So this Fe3 plus cation comes from FeOH3. Cl, I know it's Cl3, but that's because of the charge on iron. So Cl minus comes from HCl. So this salt is actually created when FeOH3 and HCl react, undergo an acid-base reaction, a double replacement reaction. So now we just need to label each part, each base and acid, to figure out what that means about the cation and the anion. FeOH3, again, look on your periodic table. Is iron part of the lowercase b on the periodic table? No. Iron then is not a strong base, so iron is a weak base. Iron 3 hydroxide is a weak base. HCl is one of your 7 strong acids. So then we can kind of work backwards. If FeOH3 is a weak base, its cation is a weak acid. If HCl is a strong acid, Cl minus is neutral. So now we compare what we wrote down up here. Part of the salt is acidic, part of the salt is neutral. Well, neutral we ignore. So part B, FeCl3, is an acidic salt. So if we look at part C, let's look at part C. Part C, it says Na2CO3. All right. So if I split this, again, the cation comes from the base. So Na will come from NaOH. Let's look at the periodic table. Is Na part of the lowercase b on the periodic table? Yes, right? It's group 1, and then calcium down makes that lowercase b. Any of those metal ions with hydroxide creates a strong base. So if NaOH is a strong base, that means that its cation is neutral. And then CO3, so we add an H to figure out what the acid is. CO3 actually comes from HCO3 minus, because the anions are actually the conjugate bases of an acid. So HCO3 minus It's not one of my 7 strong acids, right? So it's weak. So if HCO3 minus is a weak acid, that means that CO3 2 minus is a weak base. So for part C, we have a neutral cation and a basic anion. Neutral doesn't matter. So that means that overall part C is basic. And then if we look at part D, KClO4. So here's what I want you to do with part D. Split it up and see if you can write which base the cation comes from and which acid the anion comes from. Just split it up. Practice splitting it up. So when you practice splitting it up, remember that the cation comes from a base. So you add OH. Comes from KOH. KOH, potassium is part of that lowercase b. So KOH is a strong base. KOH is a strong base. That means that K plus is neutral. ClO4 minus comes from HClO4. HClO4 is one of your 7 strong acids. So if HClO4 is one of your 7 strong acids, that means that ClO4 minus is neutral. So both of them are neutral. Means we have a neutral salt. Again, if we kind of work backwards, an acid-base reaction is a double replacement reaction. So when I have KOH plus HClO4, my positive ions switch. So H will combine with OH to produce water, and then K will combine with ClO4 to create KClO4. That's how we're looking at the acidity or basicity or neutrality of salts. We're going backwards. We're looking at the acids and the bases that they come from. And then finally, part E. So part E, we have NaHC2O4. So we have NaHC2O4. So if we take a look at this, Na comes from NaOH. Right? Na comes from NaOH. Now, if I focus on NaOH, this is a strong base, which means that Na plus is neutral. Now, HC2O4 is unique. HC2O4 is unique because this is an amphoteric substance. This is amphoteric. Remember that amphoteric means that it can act as an acid or as a base. When you have an amphoteric substance, we actually have to compare the Ka and the Kb value to see whether it will act as an acid or as a base. So here's what I'm going to do. I'm going to give you the 2 values that we need to compare. So the Ka value of HC2O4 minus is 6.4 times 10 to the negative 5th. The Kb value for HC2O4 minus is 1.7 times 10 to the negative 13. So again, both of these are for HC2O4 minus because it can act as an acid or it can act as a base. So to figure out which one it's going to act like, we have to compare the Ks. Whichever K is greater, that's how this will behave in the salt. So if you look at the K values, Ka, right, and you would be given the Ka values. You'd be given the Ka values to compare if you needed to compare them. E is more so an advanced type question. You would see more questions like A through D, right? You would see questions like A through D. E is definitely a more advanced question. So you have to compare the Ka and the Kb of this amphoteric substance. Whichever one is greater is how it will behave. So if we take a look, Ka is times 10 to the negative 5th. Kb is times 10 to the negative 13th. Ka is a greater number. Ka is a greater value, which means that this will act as a weak acid. So since the Ka value of the hydrogen oxalate ion is greater than the Kb value of the hydrogen oxalate ion, hydrogen oxalate will act as a weak acid. You only have to do this with Ka values when the substance is amphoteric. And I know that it's amphoteric because it's HC2O4-. So it has a proton that it could donate, but it also carries that negative charge, so it could accept a proton as well. So you only have to do that when you have an amphoteric substance, something like this, HS-, anything like that. So since we have neutral and weak acid, this salt will actually be acidic. Again, in part E, we had to do what we did because HC2O4- was an amphoteric substance. So we needed to figure out, will the amphoteric substance behave more like a weak acid or more like a weak base? Based on the Ka and the Kb values, Ka was greater. So hydrogen oxalate will act more as a weak acid, which is why the salt is overall acidic, because Na+ is neutral. Okay, so as you look through example 20, why in part C? So you could actually, so for part C, you could have done either HCO3- or H2CO3. Either one actually would work, and because they're both weak acids. So they're both weak acids, which would make CO2- a weak base. So H2CO3 would be an acceptable like acid to look from as well. Yeah. Yep. Yeah, and it's Na2 since it's CO3 2-. So the 2 down here is because of the charge on the carbonate ion, but you could have written HCO3- because that would have one additional H, or you could have done H2CO3. They're both weak acids. Yeah, so it wouldn't have affected our overall salt. Any other questions as you're looking through example 20? And again, example 20 takes lots of practice. So you can see that I'm recording the meet. So if you need to go back and you need to refer to any of these, you can. But you now have time, so about 35 minutes that you can work on mastering. I would suggest working through the numbers that match the examples we've done. So today, number 20, or example 20 matched number 37 on mastering. And then example 16 matched 28 and 34. And then yesterday we did lots of examples that matched 6, 7, 9, 22, 26 on mastering. But if you're not sure of a question, right, we'll work through more examples so you don't have to guess. If you have questions, I'm going to stay on until probably about 9 o'clock, and then I'll get ready for third period. You can see I'm trying to give you work time on mastering each day. The very last thing is for tomorrow, you're going to watch the last video in Unit 7, which is 7.5.